Hello students, in this video we'll see an example of how to use the rational root theorem in a situation where there are repeated roots. So let's consider the following ODE. Let's consider the ODE. 12y triple prime minus 28y double prime plus 19y prime minus 4y equals 0. So we have a constant coefficient ODE. So a constant coefficient which means we can factor the ODE and hope to find the roots of the essential ODE that way. So if we rewrite this as 12d cubed minus 28d plus d squared plus 19d minus 4 applied to y equals 0. We can use the rational root theorem to test what roots we might possibly have. So our possible roots, our possible rational roots, are plus or minus the factors of the constant coefficient, 4, over the factors of the lead coefficient, which is 12. So we'll have plus or minus 1, 2, and 4. Those are the factors of 4 over 1, 2, 3, 4, 6, and 12. Those are the factors of 12. Now we would have to systematically check every one of these individually to see which ones are the roots. So let's test 1/2. If we test 1/2, we'll put 1/2 in the box, and then we'll have a 12, a negative 28, and then a 19, and a negative 4. We'll bring the first number down, 12. So what we'll have is we'll have 2 times 12, that's going to be a 6. Then I'll have a negative 22. Then a half times negative 22 is negative 11. 19 and negative 11 is 8. 1/2 and 8 is going to give me a 4 and a 0. And so what that tells me is it tells me that we have a root, right? So 1/2 is a root, which allows me to factor d minus 1/2 and then 12d squared minus 22d plus 8 applied to y will be equal to 0. So we can write our differential equation in this form. Now what we can do is we can factor this over here. So what we will have is we'll have a d minus 1/2. And out of these terms, I see a common factor of 2. So I will pull out a factor of 2 from this. And I'll be left with 6d squared minus 11d plus 4 applied to y is equal to 0. And I can rewrite this first term over here as 2d minus 1. And now we can factor this expression over here. I can factor it as 2d and 3d. And I need to get to negative 11. So what I'll do is I'll put a negative 1 over here and a negative 4 over here. And that will get me to negative 11. Applied to y is equal to 0. So I factor the equation. Now we see from this, by cycling these, that I'll get two solutions. The first solution I will get from this term over here is I'll get y equals c1 e to the 4/3 x. These other solutions over here, this factor over here will generate y equals c2 e to the 1/2 x. The problem is that I now have a repeated root, and so I can't use this other factor to cycle through and get the other ones. So now what we do is we do the following. So we say that if, so a factor d minus a squared applied to y equals 0. An equation of this form where I have a repeated root of multiplicity 2 has solution y equals c1 e to the ax plus c2x e to the ax. And this follows by reduction of order. This is proven using reduction of order, which we'll see in a future video. we can apply this proposition or this result about repeated roots to this cumulative factor over here. I have a repeated factor of e to the 1/2 x. So from this proposition together with this factorization, I see the general solution of our equation will be c1 e to the 4/3 x plus c2 e to the 1/2 x. And finally, c3 x e to the 1/2 x. So I get this extra additional factor of x out in front of the repeated root coefficient in my factorized differential equation. Thank you very much.